In this lab, we're going to delve into the force of gravity, something that we are all familiar with, but something that we tend to take for granted. Here on Earth, basically everything is pulled down by gravity. You can't really avoid it. You can't really get away with it. It's what keeps everything on the surface of the Earth, and it's the force that brings everything towards the center of the Earth. Now, to us, the center of the Earth is so far away, we'd never even think about it, so it mostly just kind of gets simplified to we're pulled down to the surface of the Earth. But gravitation is basically just a force that brings one massive object towards another. Anything with mass can attract anything else with mass in kind of the classical terms of physics. Just depends on how close they are, is how strong the attraction is, as well as how much mass is actually there. In order to actually feel something, we have to have something pretty dang large, like the size of a planet, which Earth is. So Earth has a strong gravitational pull on us, which keeps us down to the surface of the Earth. And whether you are at sea level or somewhere a little bit lower or above, it's pretty consistent how the force of gravity acts on things. Now, that might make you think that the force of gravity that is affecting this guy here versus this guy is the same force. But I can feel more force from this pushing down on my hand than I can from this, okay? It's what we usually refer to as how light or heavy something is, or its weight. Weight is really just a way of saying the force of gravity. When we measure our own weight in pounds, that takes into account how gravity is pulling down on us. If you want to talk strictly about just how much stuff is there, like how much stuff you're made of, that's mass. But weight is technically about that mass being pulled down by gravity. Now, the usual example that gets thrown out with this is, your weight would be different whether you are on the moon or on Mars or on Earth, based on how gravity pulls you down and pulls on your amount of mass. But your mass would be the same no matter where you are in the universe, because it doesn't depend on how gravity pulls on it and what the force is in the end. It's basically just how much stuff you're made of. Okay? So really, the force of gravity is another way of saying something's weight. Okay? The force of how much we are pulling down based on how much stuff is there. So the force of gravity is going to be perceivably different for something that has more mass versus less mass, even though it seems like we should have something pretty constant with gravity. Since it should be pulling on everything the same, we think, okay, we should have the same force. But it should make sense that if there's more stuff to pull on, then the force should be stronger, right? So what's constant about the force of gravity is not actually the force itself, but how it accelerates objects. We're going to see that in this lab today, about how different objects are accelerated the same by gravity. And even if you go up really high in the mountains, or again, you go really, down to sea level, this is pretty consistent no matter where you are on Earth. The way that something is accelerated by gravity is basically the same no matter where you are. It comes down to a couple decimal points off depending on where you go, but for the most part, it's pretty consistent. And it's definitely going to be pretty consistent just based on the instruments we're going to be using in the lab, which aren't as precise as some super technical machinery that's out there in science labs. So we're going to be using one of these spring scales, which just has a spring on the inside, and it's calibrated so that when something pulls on this spring, it moves. There's a little kind of, I don't want to say platform, but like a flat piece on your spring scale that shows basically what force reading you are at. The N stands for newtons of force, since Isaac Newton kind of figured out a lot of stuff with motion and the laws of motion with forces and stuff. He got his name slapped on this. So in the US system, we call force pounds, like your weight. But in the metric system, we use newtons. Okay, so the more force that's pulling down on this scale, the farther down we're going to go here, and the more newtons of force we're applying to this. So we're going to have our force applied to this spring and pulling this down by just a mass hanging on it, not physically us pulling on it, but allowing the force of gravity to do that for us. Okay, again, different masses should have different forces as a result of them being pulled down by gravity. So this mass, pull it down about halfway, if you kind of take note. Okay, it's about halfway down the scale. Just maybe about 5 newtons. This is a 10 Newton scale. Okay, this guy maybe only like a tenth of the way down the scale, maybe down to like 1 Newton or so. Oops. And then we have this guy, ooh, which is just barely enough for the scale to make it. This is hitting about 10 newtons. So, the force we exert on our spring scale, okay, is going to be just based on the force of gravity. We're not going to be adding any extra force by physically pulling it down. We're just going to let the weight of the object do the work for us. Okay? So all I have to do is hang up your spring scale on a clamp somewhere, so it's hanging freely. You might check and make sure it's calibrated, so if there's nothing on the scale, then it should be reading 0 newtons because there's no force pulling on it. If it's a little bit above or below that, you might ask your teacher and they can adjust it using this nut here at the top. You can kind of screw it back or forth to change where your spring's initial position is or how it's pulled initially. If you're not careful, it can get kind of messed up, so again, I would leave that to your teacher to do. Okay, and then all you have to do is pick some different masses. It doesn't really matter which mass you pick, so have fun, just going around and figuring them out. Although, if you pick a mass that's a little too light, like this little dinky guy that's like 10 grams, you might not be able to tell what the reading is if it's such a small change. It looks like it didn't even move, So, you might experiment with a couple and pick ones that you can definitely tell the force reading on for those different masses. Now, these masses are labeled in grams. Sometimes the labels get worn off a little bit, so you might go and compare it to a weight of another set, or ask a teacher, or maybe one of these days I'll actually write in some new labels for it or something like that. But keep in mind that we're going to be using kilograms for this. Our equation using force is that force is equal to mass times acceleration, and that mass has to be in kilograms for the equation to work right. That's what the way it's kind of set up, the way it's built. So make sure that you convert your grams into kilograms before you do any number crunching to calculate the acceleration of gravity. That should be pretty constant no matter which mass you use. Okay, so a couple things to keep in mind. Again, doesn't matter which mass you pick, but make sure you convert it to kilograms. You can do this by dividing by 1,000. You could set up a conversion factor. You could move your decimal point 3 spots to the left, but it all basically comes out the same way. Okay, it accomplishes kind of the same thing. Another thing is to make sure you use the right version of your force equation. Usually it's set up as force is equal to mass times acceleration, but in this case, we're already measuring the force, so it's not like we need to find what the force is going to be and calculate it. We're going to have what that force already equals. We're going to know the mass in kilograms. You're going to make sure to convert it, and then we want to solve for the acceleration instead. So make sure you use a version of the force equation that has A equals. Acceleration equals something to do with the force and the mass. Now, you should find that whether we're using a large mass or small mass or a bigger or smaller one, that we're going to end up with about the same acceleration from gravity. So if you are calculating A equals and you keep getting your acceleration equal to about the same thing every time you do it, no matter which mass you use, you're on the right track. Keep doing that. Okay? If you keep getting wildly different answers, like maybe at one point it's 0.2 and then another time it's like 8,000, you might go back and check your work and see what went wrong, because it should be coming out about the same every time. We're going to find that our acceleration is fairly constant for gravity here on Earth. Okay. Now, in order to kind of help to verify these results, we're also going to use a simulation that basically is an online digital interactive version of this, with this spring scale. So the actual use of the program is not as fun as actually doing this in the lab, where you actually get to pick out a mass and hang it. But it does give us more accurate results because it will calculate some things for you. For example, you won't actually have to read off the little lines on the scale on your computer screen. You'll just be able to see what the force readout is exactly out to 2 decimal places. Same goes for your mass, which will already be given in kilograms. And it'll also give you grams off to the side. But kilograms is the one we want. Remember, make sure to use kilograms. Okay, so with the mass and the force given so precisely out to a couple decimal places, that will give your acceleration calculations a little bit more accuracy compared to just trying to do our best to read off of this here. So you should be able to compare kind of both and see if your answers are lining up. And they should be pretty close to the same, whichever you're using, like the physical lab part or the simulation part. But this way you can kind of verify your results and also see kind of the benefits of either way, either doing it digitally or physically.